Hi, I hope that you are doing great. Before starting the lecture, I think that mentioning some points would be in order. This is the first video that I have produced based on the course Linear Algebra and Geometry with the code number SF1624 presented at KTH, Royal Institute of Technology, Stockholm, Sweden. This is a course in elementary linear algebra. This video starts on Module 4, starting on Chapter 4 of the course book, Contemporary Linear Algebra by Howard Anton and Robert C. Bosby, 2002. This is a fairly long video since I could not find a suitable point to split the video. The primary goal of this first lecture is to make the definition of a determinant, which at first glance might seem very artificial, look natural. Now, some practical points. In the descriptions below the video, you find 5 links. The first link gives you access to a PDF file containing a number of problems, including the final answers where applicable. Some questions are chosen directly from the course book, some from the other textbooks, and some are designed by myself. You can find the title of the textbooks used at the end of this PDF file. I will also include some exam questions from the past exams for the course at KTH whenever I find interesting questions applicable to the material covered in that particular video. My intention is to upload another video in which I will discuss and solve all these problems in detail. There is, of course, only one way to learn mathematics, and that is to do mathematics through solving more and more problems. The second link is the link to the PDF file of these notes that right now you see on your display, and in this lecture I will write down my explanations in between empty spaces that I have already provided in the file. So this, you see, this is the file. So you see that whatever I want to cover in this lecture are already written, and there are some empty spaces provided, for example other pages as well, and then I will start solving and giving my lecture, and I will fill up these empty spaces with my explanations and solutions. In this file, the solutions to examples that I will present in this video are not included. I use iPad Pro together with Apple Pencil and GoodNotes 5 application to produce these videos. The content of the third link is exactly the same as the second one, except that this one is the GoodNotes file. I strongly recommend you to have one of these files available when watching the video. If you have access to a tablet with GoodNotes installed on it, then you can use the third link to download these lecture notes directly onto your tablet, as if you yourself have created them in the first place. Otherwise, you can use the second link to download the PDF version of these notes and print them. I think having the notes in front of you while watching the video could be very helpful in active learning. The fourth and fifth links are links to PDF and GoodNotes file accordingly of these lecture notes again, but they contain all my solutions to the examples and all my written explanations that will be presented by the end of this video. I spend many hours enthusiastically to make these videos available for free. If at the end you found the video somehow helpful and enjoyed watching it, I will be very happy if you can invite me with a thumb up. By subscribing to my channel, you will be immediately notified if I upload a video. Okay? So now I think we can start the lecture. Okay, after this introduction, let us just go directly to the lesson for today. In this video, I'm going to introduce you the notion of a determinant. Determinants play a prominent role in linear algebra. Actually, a determinant is a number that we associate with a square matrix in a way that becomes clear by the end of this and coming lectures. A determinant can be 0, positive, negative, or even a complex number, if the matrix, of course, includes complex numbers as entries in the first place. Anyway, in this course we will not consider matrices with complex entries. You might be familiar with the definition of a determinant from your previous studies. At first glance, the definition of a determinant might look very artificial and clueless. My primary goal in this video and in this lecture is to convince you that, at least in the context it was first introduced, its definition is nothing less than being natural. Historically, the notion of determinant appeared in mathematics when people were studying the properties of systems of linear equations with the same number of equations as the number of unknowns. And they wanted to derive suitable formulas in order to determine the solutions to this kind of systems. So let us start with an example to make things a little bit more clear for you. So example 4.1. Let me read the example for you first. Consider the following system of equations. 2 equations, 2 unknowns, x1 and x2. Where bi's and aij's are given real numbers. Determine x1 and x2 in terms of these real numbers. Okay, so this is a simple algebraic problem. The algebra is very simple, but let us do it once together. It's instructive from my point of view. Okay, so if I want to solve the system, that's a high school problem, I just do addition method here. So for example, I would multiply the first one by a22 and I will multiply the second one by minus a12. Yeah, so let me write this here for you. So then if I multiply this, it becomes a22 a11 x1 plus a22 a12 x2, and on the right hand side I will have a22 b1. For the second one I will have minus a12 a21 x1 minus a12 a22 x2, and I will have minus a12 b2. Yes. Now my goal is to add them side by side. If I add them, this term and this term are exactly the same with opposite signs, so they are cancelled, and I will factor x1 out from this one. So then I immediately get that I will have a11 a22 minus a12 times a21 times x1, and on the right hand side I will have b1 a22, and then I will have minus a12 b2. Yes, so I add these two together, I got this. I add these two together, I factored x1 out, and I got this. Now, assuming that this is not this coefficient, if this coefficient is non-zero, then I can divide safely both sides by this coefficient. So what I get is that x1 becomes equal to b1 a22 minus a12 b2, and then I will have the denominator a11 a22 minus a12 a21. Yeah, so this is what I get by algebraically solving this equation. And I don't want to spend time on it. You can do the simple algebra yourself. You will get a very similar formula for x2. Just let me write down the formula here for you. The formula turns out to be a11 b2 minus b1 a21, and the denominator turns out to be exactly the same denominator as before. Okay, so you got this one. Now let us have a closer look to the structure of these formulas here and here. We immediately realize that the denominators for x1 and x2, as I said before, are exactly identical. Let us denote these common denominators by a symbol, yes? And the symbol that is used here is this symbol. So let me introduce you this symbol. I would write this symbol a11, a12, a21, a22, and I put a semicolon and equality here. It means that it is defined to be equal. This means defined to be equal, and I define it in the exact. I will take this common denominator as the definition of my symbol. Yes, so I would write a11, a22 minus a12, a21. So this I will take it as the definition of this symbol, which of course I will call it a 2 by 2 determinant. Okay, now let us consider the numerator of, say, x1. So let us concentrate here for x1. You see that the structure of its numerator is similar to the structure of its denominator. You see, this is the difference of a product, two products, the difference of two products, the difference of two products. Okay? And each product contains exactly two factors. So they have the same structures, similar structures. It's also if you look at the first term of the numerator and the first term of the denominator, the first term of the numerator and the first term of the denominator, you will see that a22 is the same, but a11 has been replaced by b1. Now let us go to the second terms, compare them. a12 is the same, but a21 has been replaced by b2. So what does it mean? It means that the numerator also can be expressed as a 2 by 2 determinant. Yes? But the only difference is that a11 has to be replaced with b1, and then a21 has been replaced, a21 should be replaced by b2. And then this gives you immediately the numerator of x1. So the numerator of x1 can also be expressed as a determinant. So it becomes the determinant of b1, b2, as I told you before, then a12, a22. Yes. So finally, what I get is this. You see, x1 is this. The denominator can be expressed in terms of a 2 by 2 determinant. The numerator also can be expressed in terms of a 2 by 2 determinant. So what I get is a nice formula. x1 is a fraction whose denominator is this determinant, and the numerator is also another determinant. Exactly similarly, following exactly the same ideas, you will get a similar formula for x2. Yeah, so that is your formula for x2. Okay, so let us summarize what we have got so far. I have done it in the next page, and I call this the memory stop. I want you to memorize the formulas after understanding them. Yes, so we realize that if I have this system of equations in which these numbers are all given real numbers, provided that this symbol, this determinant, 2 by 2 determinant, is non-zero, then x1 can be expressed as a ratio of two determinants and x2 the same. And then let us see. The denominators are exactly the same determinant, and the entries are exactly these coefficients here, here, and here, here. But then if you want to find x1, you will replace the first column by b1 and b2 here. But you do not touch the second column. And if you are interested in calculating x2, what you do is that you replace the second column by b1 and b2, and you will not touch the first column. Okay? Okay, so hopefully I could convince you that introducing this symbol, which we call it the determinant of this matrix in the future. So you see that I can have a matrix in this form. I have the square brackets here. Yes. Later we will call this the determinant of this matrix. Hopefully I could convince you that introducing this determinant symbol is useful and enables us to write the formulas regarding x1 and x2 in an organized way that, as we will see shortly, can easily be generalized. This phrase is important. Can easily be generalized. Before going any further, I think that it could be instructive if we solve a very simple numerical example. Okay? So assume that I want to solve this numerical example using what I actually got here in the formulas. So let us do it very quickly. This is a simple problem. So I want to calculate x1. According to the rule I told you that I have a fraction, the numerator and the denominator are determinants. For writing the denominator, I take these coefficients and then I would write it here. So then it becomes 3, 4, 5 minus 3. In the numerator, since I am interested in calculating the first unknown x1, I have to remove the first column and replace it with 7 and 8. So it becomes 7 and 8. And then I will not touch the second column. So it's 5 and minus 3. Okay? So what happens? I need to calculate this determinant. I told you what is the definition. I need to multiply these two numbers. I need to multiply these two numbers and subtract them. And the same for the denominator. So it becomes 7 times minus 3 minus 5 times 8. And the same for the denominator. Yes, so the numerator becomes minus 21 minus 40, and then I have minus 9 minus 20, so it is minus 29, and then I have 61, and the minus signs are cancelled actually, so I cancel the minus signs. So it means that x1 is actually 61 over 29. Yes, and then if I want to calculate x2, the denominator of x2 is exactly the same determinant, but the numerator is another determinant such that, because now I am interested in x2, I will remove the second column and replace it with 7 and 8, but I will keep the first the same. So it becomes 3 and 4, and then I will write 7 and 8. And then the denominator is exactly as before, so I don't need to calculate. It's minus 29, but the numerator is 24 minus 28, so it's minus 4. It becomes 4 over 29. So it means that x2 is 4 over 29. Yes? Okay, so I think everything is clear. What is the motivation is that at least at this point you understand that the symbol we introduced was indeed useful. Okay? Now let me ask you this. Assume that you yourself want to define a 3 by 3 determinant, as I have written here. Yes, you want to define this object 3 by 3 determinant on your own. Where do you think would be a suitable starting point? I'm sure you could guess correctly. We felt the need to introduce the notion of a 2 by 2 determinant when we wanted to write the algebraic formulas expressing the unknowns of a system of two equations in two unknowns in an organized and easy to remember way. So to define a 3 by 3 determinant, you might have guessed that a possible and natural starting point would be to look at the algebraic formulas that express the unknowns of a system of equations consisting, this time, of 3 linear equations in 3 unknowns. If that is your guess for the starting point, congratulations, your guess is perfectly fine. Actually, your guess is the content of the next example. Okay, so let me go to this page now. So, example 4.4. Consider the following system of equations. Yes, this time I have 3 equations and I have 3 unknowns, x1, x2, and x3. Where, again, as before, bi's and aij's, these numbers, coefficients, and these constants are all real numbers. Determine x1, x2, and x3 in terms of these real numbers. Okay. The algebra needed to get the formulas for x1, x2, and x3 is elementary as it was for the previous case, but of course expectedly more tedious because of more number of equations and unknowns involved in this case. I leave the algebra as an exercise to you and just express each formula in its final form. Okay, here you are. These are the formulas. To save time, I have already typed them here for you. Okay? Okay, so let us ponder over these formulas for a while and try to explore their structures. Okay, so let us look at these formulas more closely and try to explore their structures. The first point that comes into sight is that the denominators, again, as in the previous case, are all identical. You see, the denominators are all identical. Motivated by the previous case, we define the 3 by 3 determinant to be the denominator common to all these fractions. Yes. So, yes, here, this is the definition. This is the, you see, this expression here on the right hand side is the common expression for all the denominators. Now I am saying that I take this as the definition to this 3 by 3 determinant. Okay, let us now explore to see if this definition is as useful as it was in the previous case. In other words, let us see if this definition for a 3 by 3 determinant makes it possible to rewrite these messy relations in a more organized way. Yes. To do this, let us have a closer look at the algebraic structure of each of these fractions. For definiteness, let us consider the case of x1, and let us compare its numerator to its denominator. Yes, we focus here on the first fraction. My goal is to compare the numerator and the denominator of this fraction together. We immediately realize that, of course, they have again very similar structures. For example, both of them has 6 terms. You see 1, 2, 3, 4, 5, 6 terms in the numerator, 1, 2, 3, 4, 5, 6 terms in the denominator. And each term consists of 3 factors. So for example, this term has 1, 2, 3 factors and the other one as well. And here I have 1, 2, 3 factors and the same for others. 3 with positive signs, you see positive, 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 positive. And 3 of them are negatives, yes. So they have very similar structures. It is easily seen that if in the denominator we replace A11 by B1, A21 by B2, and A31 by B3, okay, so let me write it for you here. if I replace a11, let us concentrate, so what I'm saying, let us concentrate on this fraction. And I'm saying that if in the denominator you go and replace a11 with b1 and a21 with b2 and a31 with b3, so you immediately realize that you will get the numerator. So let me try to convince you somehow. So look here. I want to do this one first. I have a11 here and a11 here. If I replace a11 with b1, what happens? This a11 becomes b1, and then you see that a22 is the same, a33 is the same. And again here, a11 turns into b1, and a23 and a23, a3 and 2 and a3 and 2 are exactly the same. Okay, so this means that by just this replacement, the first term turns into the first term, and the last term turns into the last term. And for example, let us do one more case, a21 to b2. Here, I have a21 here. If I change a21 with b2, you see a13 is the same, b32 is the same. So if I do this replacement, this term will actually transform to this term. And then there is another term here containing a21. a21 will be replaced by b2, and then these are exactly the same. So by this replacement, these two terms will actually be transformed into these two terms. And then if you finally do the last one, the other left terms will actually transform to the other ones. So in principle, I hope that I could convince you that by these three replacements in the denominator will change into the numerator. Okay? So what can I say is that, you see, this was the denominator. I defined it by this symbol, and then I convinced you that the numerator is the same denominator, except that you have to replace a11 with b1, a21 with b2, and a31 with b3. So it means that what happens is the numerator of x1 is the same as the denominator with these replacements. Yes. So instead of a11, I put b1. Instead of a21, I put b2. And instead of a31, I put b3. So what I get here is exactly the numerator of x1. So it means that this implies that the x1 that I am looking for is the numerator of x1, which is this expression, I put it here, divided by the denominator of x1, which is this expression, and this is equal to that. Yes? Following the same line of arguments, one can easily get to similar formulas for x2 and x3. Okay? So, let us summarize what we got so far for the 3 by 3 case. Okay, I have to go to the other page. Yes. So this is what we got for the case of 3 by 3 case. So here you see, I also called it a memory stop. So if this determinant, this symbol, is not equal to 0, and you're supposed to solve this system of equations, then these are the formulas for x1, x2, and x3. And you see that the same pattern that we have for the two equations in two unknowns actually emerges here again. You see, the denominators, all of them are identical, and they are equal. If you want to fill this determinant, you need to take these coefficients and put them here and here and here. Yes? But if you are interested in calculating x1, you go and replace the first column by these numbers here, and you get this column in the numerator, but you will not touch these columns, the second column and the third column. Let us do once more here. So for example, I am interested in x2. The denominator is as before. The determinant of consisting of these coefficients as before. But now, because now I'm interested in the second variable, what I do, I replace the second column by these numbers, and then I will get the second column in the numerator, and then I will leave these two columns intact. And the same scenario for x3. Okay, so hopefully you are now convinced that the definition of a 3 by 3 determinant as we introduced it here is worthy, since at least it provides us with a means to express the formulas in an easier way. Okay, so by the way, the French mathematician, so let me write the name. The French mathematician Pierre, let me make sure that I am doing it correctly, yes, Frédéric Sarous, hopefully my pronunciation of this French name is recognizable by native speakers, discovered a mnemonic rule to remember the definition of a 3 by 3 determinant, and that is his rule. Yes, so he's saying that if you want to calculate this determinant, it's hard to remember this. So this is a mnemonic rule that helps you to remember this a little bit complicated formula. So what he is saying is that, so this is the determinant that you are supposed to calculate. So assume that this is your determinant. You want to calculate this determinant. You need to repeat the first and second column besides your original determinant. And then this is your main diagonal of the matrix, and then you draw two other parallel lines here, and you do the other way around. Okay, what we need to do with them, I multiply these numbers, I multiply these numbers, and I multiply these numbers. This positive sign means that I need to keep the sign as I get with this product. If the product is positive, I keep it positive. If the product is negative, I keep it negative. And then after that, I do the same thing for these somehow diagonals, yes, in the other direction. And I multiply them, yes. But what happens, I have a negative sign for all of them. It means that if this product turns out to be a positive, I make it negative. And if this product turns out to be a negative, I put the opposite one, I put positive. And then, so I get 6 numbers, one this product, this product, this product, and I will get 3 other numbers from these products, and I add them. And of course it's not a breakthrough, yes, it's not that hard to see this, but that's a very nice mnemonic to remember the formula. So here, you see, for example, A11, A22, A33, if I multiply them, it will give me this. And if I multiply A12, A23, A31, it gives me this. And then the same thing here, you can immediately see that this will give me this. And hopefully you can convince yourself, for example, here A13, A22, A31 is exactly this term, and you see this is negative, so we have a negative here. So for example, if you want, I can give you a quick example here. So let me just change this a little bit, put it here for you. So for example, if I want to calculate the determinant of, I don't know, 2, 3, 1, 0, 1, 2, 1, minus 1, and minus 1. Yes. So what I do, I would write, I would repeat the first 2 columns here, 2, 0, and 1, and I will have 3 and 1 and minus 1. Yes. So then what I do, I would, let me change the color here. So I will consider this, I will consider this, and I will consider this as a product. So if I multiply them, so here you see that 2, 1, and minus 1 gives me -1. Okay, so let me write -1 on top. Then I will multiply these three. 3, 2, 1, it gives me 6. So I would write just 6. And if I multiply the next 1, 0, 1, -1, it becomes 0. So it becomes 0. I put it here. And then I go to the other direction. So here, for example, and here, and finally here. But this time I need to remember I have to change the signs, yes? Put the opposite sign. So here, for example, you multiply 3 by 0 by -1, it becomes 0. So -0 is just 0, so no problem here. And then I have 2 times 2 times -1, which is -4, but I put +4 here. Yes, and then I multiply 1 by 1 by 1, it becomes 1. I put -1 here. Yes, and then what I do, I add all these numbers. So what happens? It becomes -1 plus 6 plus 0 plus -1 plus 4 plus 0. So it becomes 4, 4, 8. Yes, so this is the determinant. But please remember this remark. Let me see. Oh, sorry, I made a mistake here, so let me fix that one. I don't know. Here I multiplied -1 by 1 by 2, and then I wrote -1, which is actually a mistake from my side. Sorry. So this is -2. So this becomes -2. Then what happens is that this becomes -2 as well. So I will have 7 now as my answer. Okay, so let me fix it. Sorry. So the final answer for this is actually 7. But what I want you to remember is that this remark, the Sarus rule, works only for 3 by 3 determinants. So you're not allowed to use this rule for a 2 by 2, 4 by 4, 5 by 5 determinants. This only works for 3 by 3 determinants, okay? Okay, so we learned that the formulas for the unknowns of systems in 2 and 3 unknowns can be written in a simple and organized way if we introduce 2 by 2 and 3 by 3 determinants. Of course, this is not the main reason that these definitions are valuable. The main reason is that these definitions illuminate that how one can generalize the theory of linear systems to a theory of systems including an arbitrary number of equations and unknowns. For example, if I give you the following system consisting of 4 equations and 4 unknowns, then I'm sure that you can immediately guess the correct formulas expressing x1 to x4. Yes, they are actually these formulas that you see here. So you see that we have this common term determinant in all the denominators, and say for example I am interested in calculating x3. What I'm doing, I am just replacing the third column, this third column, by these constant numbers here, but I do not touch the other columns, and the same for the others. So as you see, all the formulas deal with 4 by 4 determinants. Of course, the point is that how a 4 by 4 determinant should be defined in the first place. Okay, let me ask you this question. What is your strategy to define a 4 by 4 determinants? So how do you define this object that appears in all these denominators and similarly in the numerators? How do you define? What is your strategy to define such an object, mathematical object? Yeah, at this stage you might still want to follow the previous strategy. Namely, you might say that we solve the system algebraically, and if everything goes as it went for the previous 2 cases, We will then get an identical expression in all the denominators of all fractions expressing x1 to x4, and we take that expression as the definition of this 4×4 determinant. Yeah, sounds reasonable. But can you see the disadvantage of this strategy? This argument relies on an if statement, and from mathematical point of view, this if is indeed a big if everything goes as it went for the previous two cases, yes? Of course, there is no guarantee that this is indeed the case. How do we circumvent this drawback? Roughly speaking, we reverse the logic of how to approach the problem. Let me explain what I mean by reversing the logic. We first investigate the definitions of 2×2 and 3×3 determinants term by term and try to figure out a unified rule that underlies both definitions. We then declare this rule as the defining property of determinants, and using this property, we introduce a unified definition of all determinants of all orders. Using this unified definition, as you will see in coming lectures, we will discover some interesting properties that determinants enjoy. Determinants now as an abstract mathematical concept and entity. These properties will then enable us to derive the general formulas that express the unknowns of any linear system consisting of n equations in n unknowns in terms of n by n determinants whose entries are the coefficients and constant terms of the system. These general formulas, as we will see, will be introduced as a theorem called Cramer's rule during the coming lectures. Hopefully, I could make myself somehow clear. If not, don't worry. I'll explain it again step by step. By the way, as you might know, this process that we are going to follow to define a generic determinant by first looking at some special cases and then define a concept based on the information and properties that we extract from these observations is not just for defining determinants, and is in fact a very well-known process, at least in contemporary mathematics. Known as what? Yes, it is called abstraction. To make a concept abstract, we focus on the essential features of that concept by considering, for example, some special cases, our geometric intuition, etc., etc. Then we define a new mathematical concept to be the one that exactly satisfies those features. Okay, let us go back to the job. So now our first task is to define determinants of all orders on the same footing. To make life easier, let me write the definitions of 2×2 and 3×3 determinants below each other. By the way, I forgot to talk about 1×1 determinants. Let us do it here. I think it's very useful at this stage. So let me do it here and then we go back to what we wanted to do. Let me ask you first, what do you think about how the definition of a 1×1 determinant, so for example, I want to write this. How do you think we should define this object, this mathematical object, determinant of A11? Notice that here I am using this symbol to denote a determinant, not an absolute value. This notation, I would say, is rather unfortunate, but this will never give rise to any confusion since we will almost never talk about 1×1 determinants, and if we do, it would be clear from the context which one we mean. And on top of that, we will also introduce an alternative notation for determinants, as you will see later. Okay, how do you define a 1×1 determinant? my goal is to give a definition, a reasonable definition to this mathematical object. Yes, you're right. To define a 2 by 2 determinant, I started by considering a system of two equations in two unknowns, and to define a 3 by 3 determinant, I started by considering a system of three equations in three unknowns. So, to define a 1 by 1 determinant, a natural starting point, I would say, is to consider a system, if I can call it a system in the first place, of one equation in one unknown, right? So, I will consider a system of one equation in one unknown, yes? Something like this. But we never write these curly brackets if we have only one single equation, yes? And then I start solving it as before. So when I solve this, I will get x1 is equal to b1 divided by a11. And as before, I take the denominator to be the definition of this 1 by 1 determinant. So this I will define it, I will define this object, determinant of a11, to be equal to the entry itself. So that would be a reasonable definition. And by the way, if I do this definition, again as before, this can be written as the ratio of two determinants. x1 can be expressed as the ratio of two determinants. The determinant of a11 in the denominator and the determinant of b1 in the numerator. Okay, so bottom line is that if I have a 1 by 1 determinant, the determinant is defined to be equal to its own entry, the only entry of the determinant. So for example, if I consider the determinant of -3, the answer is -3, by the way, don't get confused. This is not the absolute value sign. I am using this sign for denoting the determinant, 1 by 1 determinant. Okay. So the reason that I brought the notion of 1 by 1 determinant here is because our strategy to define a generic determinant is to look at the special cases and try to see if we can discover a pattern common to all these special cases. So by having more special cases at our disposal, we will have a higher chance to discover the pattern. Yes, so that was the idea. Now let us go back to our main task. I mean discovering the unified underlying rule governing the definitions of 1 by 1, 2 by 2, and 3 by 3 determinants. Let me repeat those definitions here for you because it's easier to have them in one place in front of our eyes, yes? This package that you can see here are all the definitions of determinants 1 by 1, 2 by 2, and 3 by 3 here. We have so far. I want to look at the terms of these determinants to try to find a pattern going on, even though they really look very different. I want to find a pattern, yes? So, let us see. As you see, the first definition contains one term, yes? Only one term. The second definition contains two terms, yes? 1, 2. And the third one contains 6 terms. 1, 2, 3, 4, 5, 6 terms. Okay, so let me write these numbers. The first one has 1 term, the second one has 2 terms, and then suddenly the last one has 6 terms. Okay? Let me write these numbers in a list for you. So 1, 2, 6, and then I have the question mark. Can you guess what number is coming next instead of question mark here? Can you see a pattern that these numbers are following it? One possibility becomes evident if you immediately realize that 1 is another name for 1 factorial. And by the way, what is n factorial? Let me recall you. N factorial is n times n minus 1 times n minus 2 up to 3 times 2 times 1 if n is greater than or equal to 2. And 0 factorial is also defined to be 1. 1 factorial is also defined to be 1. Yeah, so that is the definition of a determinant. Okay, so 1 can be written as 1 factorial, and then 2 can be written as 2 factorial, can be considered as 2 factorial. Yes, and then 6 is 3 factorial. Yes, so 3 factorial is 3 times 2 times 1, which is exactly 6. So one natural guess might be that the question mark is 4 factorial. And 4 factorial is 4 times 3 factorial, 4 times 6, which is 24. Yes. Okay, so it seems that this question mark is actually 24. Yes. This is our rough guess actually. This guess will in fact be confirmed by considering other facts that I will explain shortly. Now, let us investigate the structure of each term in these definitions. The first one, okay, contains one term consisting of one single factor. One term, one factor. The second contains two terms, these two terms, each consisting of 2 factors. So this term consists of 2 factors, 1, 2. This term consists of 2 factors, 1, 2. And the third one contains 6 terms, yes. Each contains 3 factors. So for example, this one, you see 1 factor, 2, and 3. This one, for example, 1 factor, 2, and 3. All of them. By the way, there is a definition here. Each term in the definition of a determinant is called an elementary product. So let me write it here for you. Elementary product. Yes. So these terms, for example, these are called elementary products. So here we have 2 elementary products. Here we have 6 elementary products. You see, I'm not considering the signs. I am just considering the terms. Now look. Every elementary product contains exactly 1 entry from each row of the determinant, and it exactly contains 1 entry from each column. Yes, to see this clearly, consider, for example, the case of 3 by 3 determinant. Yes, for example, let us focus here. And then let us pick one of them. By the way, you see that, for example, you see that the first indices in each elementary product are always 1, 2, and 3 in this case. You see 1, 2, 3, the first indices. 1, 2, 3. 1, 2, 3, 1, 2, 3, and etc. All of them are 1, 2, 3. So what does it mean? It means that if you pick one of these elementary products, then because I have only one term with the first index 1, one term with the index first index 2, and one term with the first index 3, it means that I have one term exactly from the first row. Here, A13 is this one, and then A21 is this one, and A32 is this one, and you see that I have exactly 1 entry from each row. So each elementary product has exactly 1 entry from each row. On the other hand, the second indices in a given elementary product consists of the same numbers, you see. For example, let us consider here, but now let us focus on the second indices this time. You see, I have 2, 3, and 1 as my second indices. But it means, so it means that all of them are actually present. 1 is present, 2 is present, 3 is present, but no more than once. Yes? So, it means that each elementary product has exactly 1 entry from each column. So this is the entry coming from the first column, this is the entry coming from the third column, and this is the entry coming from the second column. I'm trying to just give you some idea about the structures of these elementary products. Now, if you look closer, you see that if we consider all elementary products in the definition of a determinant, each possible arrangement, every possible arrangements of 1, 2, and 3 actually appears exactly once as second indices. Okay? So for example, what are the arrangements of 1, 2, and 3? The arrangements of 1, 2, and 3 are 1, 2, and 3, and then I can have 1, 3, and 2. Then I have, then I will have 2, 1, and 3, 2, 3, and 1, 3, and 1, 2, 3, 2, and 1. So I have only 6 possible arrangements for 1, 2, and 3, and all of them actually appears as the second indices. So for example, 1, 2, 3 appears 1, 2, 3 here. 1, 3, 2 appears here. 1, 3, 2. 2, 1, 3 is here. Where is it? Yes, 2, 1, 3. 2, 3, 1 is 2, 3, 1. And then 3, 1, 2 and 2, 3, 2, 1, you can convince yourself. So all of them appears exactly once. Technically, each one of these items that you see here is called a permutation. Each one of these items is called a permutation of the numbers 1, 2, and 3. Of course, rigorously speaking, a permutation is a one-to-one and onto function from a finite set onto the set itself. But we don't need that level of rigor in our definitions and presentation here. So, this is why a 3 by 3 determinant has 6 terms. Each term corresponds to one and only one permutation of 1, 2, and 3. And from elementary combinatorics, we know that the number of permutations of 1, 2, and 3 is indeed 3 factorial. So the number of permutations of 1, 2, and 3 is 3 factorial. The number of permutations of 1, 2, and 3, and 4 is 4 factorial. In general, the number of permutations of 1, 2, 3 up to n is n factorial. Okay? So this is a good confirmation about the number of terms involved in the definition of a 4 by 4 determinant. Do you remember? We told that this is 4 factorial. Yes. Now we are actually confirmed that this is a good guess. Another important issue that is, as you see, sometimes an elementary product comes with a positive sign. Sometimes it comes with a negative sign. Here, three of them come with positive signs, and 3 of them come with negative signs. Yes. Each elementary product together with its sign is called a signed elementary product. So let me write this one as well. Signed elementary product. So if you consider the sign with the product, that is called signed elementary product. Figuring out when an elementary product is accompanied with a positive sign and when it is accompanied with a negative sign is a little bit more technical. That I want to talk about now. Okay? We want to discover a pattern that the signs accompanying the elementary products obey. What is the idea? The idea is to associate a sign with every permutation of the numbers 1, 2, 3 up to n in general. So, for example, you have a permutation of these numbers. For example, let us consider the case where n is equal to 3. Consider one permutation. This is one permutation of this 1, 2, and 3. I want to assign a sign, positive or negative, to a permutation. Yes, that's the idea. To do this, we first introduce an operation that acts on a permutation of 1, 2, 3 up to n. The operation that I am talking about is called a transposition. So this is a technical term, transposition. Okay, by its definition, when a transposition is applied to a permutation, it swaps the positions of exactly 2 members in that permutation, leaving all other ones intact. For example, 1, 2, 3 turns into 1, 3, 2. That is an interchange. Why? Because 1 is not touched and then I swap the positions of 3 and 2, and I get this one. So this transformation from here to here is a transposition. For example, if I want to give you another one, so 3, 1, 2 goes to 2, 1, 3. This transformation is also a transposition. Why? Because 1 is not touched, but 2 and 3 are actually replaced, swapped, and I get this one. So that's also a transposition. For example, 3, 1, 4, 2 goes to 3, 4, 1, 2. So let us check. Here, 2, 3 and 2 are left intact, and then you see that these two only are changing. So that's also a transposition. As another example, 1, 2, 3, 4, and 5 goes to 4, 2, 3, 1, and 5. Is that a transposition? Let us check. So you see 2, 3, and 5 are exactly in their positions, but 1 and 4 has been interchanged. So that's also a transposition. But for example, so all of them, all are transpositions. Yes. But for example, I don't know, let me give you another one example. 1, 2, 3, 4, 5 goes to 2, 1, 3, 5, 4. Is this a transposition? No, you see, because not only 1 and 2 are swapped, but also 4 and 5. Yes, 3 is not changed, but 4 and 5 has been swapped. 1 and 2 has also been swapped. So that is not one single transposition. It's a compositions of two transpositions. Yes, I will talk about them later. So, but this is not a transposition. Okay. There is a theorem in abstract algebra that guarantees that any permutation of the numbers 1, 2, 3 up to n, no matter how messed up its order is, can be brought back to its natural order 1, 2, 3 up to n by applying a finite number of successive transpositions on it. So if I have this, I can immediately go back to the natural order. So for example, any one of these, for example this, can be put back in the natural order. Here, not by just one single transposition, by two transpositions. The first transposition will interchange these two. The second transposition will apply. So you see 2, 1, 3, 4, 5 goes to 1, 2, 3, it was 2, 1, 3, 5, 4. It goes to 1, 2, 3, 5, 4. One transposition. Another transposition applies on 5 and 3, on 5 and 4. It gives me this one. So you see, I was able to go from here to its natural order by applying two successive transpositions. Okay? This motivates the following definition. What is the definition? Let the sign of a permutation. Let J1, J2, Jn be a permutation of numbers 1, 2 of n. So it means J1, J2, Jn are the same numbers, probably in different orders. The sign of the permutation J1, J2 up to Jn, we denote it by Sgn of this, and it is defined as follows. We say that the sign of this permutation is equal to minus 1 to the power of n sub n. But what is n sub n? Is the minimum number of successive transpositions needed to bring the permutation J1, J2, Jn back to its natural order 1, 2, 3 up to n. Okay? So don't let the mathematical symbols distract you. You will see in the next example that the idea is extremely simple. Okay, so before going to the example, please let me mention something here. That's a definition. You see that the sign of a permutation is -1 to the power of the minimum number of successive transpositions needed to bring the permutation back into its natural order. So this is an integer, and -1 to the power of an integer is either -1 or +1. So it means that there are two types of permutations if you consider the sign of those permutations. Yes. So if the sign of the permutation is +1, it means that this number is an even number. Then we call the permutation an even permutation. Yes. And if this number becomes -1, it means that this number is odd. Then we call the permutation an odd permutation. Okay? So even permutation if the sign is +1, odd permutation if the sign is -1. Okay, now let us go to this example. Determine the sign of each of the following permutations. Okay, so what should I do? In each case, I should determine the minimum number of transpositions needed to bring these permutations back in natural order. Count the number of transpositions and then -1 to the power of that minimum transposition needed will be the required answer. Okay, so let us see how it goes. So number one, the permutation that I have here is just 1, 2, 3, and 4. Okay, so how many transpositions are needed to put this permutation in its own natural order? Nothing, yes, because this is already in its own natural order, yes. So what I can conclude is that the minimum number the minimum number of transpositions that I need to apply on this permutation to put it in natural order is indeed 0. This 4 stands for the 4 numbers. Okay, so then what can I write? I can write the sign of 1, 2, 3, and 4 is equal to -1 to power 0, which is 1. So this is an even permutation. Even because the sign becomes +1. Okay, so you see it's very simple. So number 2. So what is this? So I have 4, 3, 5, 1, and 2. So this is not in the natural order yet, but I need to use successive transpositions to put this back in the natural order. So for example here, what can I do? I can say that, okay, 1 should be here. So let us do it. Let us interchange these two. So then it becomes 1, and then I will have to keep 3 and 5 as, and I'm not allowed to touch any other pairs. So this becomes 1, 3, 5, 4, 2. Okay? So now 1 and 4 are already in the natural position. So then what should I do? I can interchange these two, for example. Then it becomes 1, 2, and then 5, 4 should be in the same place, and then I will have 3. But it's not in natural order. The last one will work. If I interchange these two, then what I get? I will get 1, 2, and then I will get 3, 4, and 5. Now it's good. Now it's in natural order. But how many successive transpositions I applied? 1, 2, 3. Yes, so this means that the sign of 4, 3, 5, 1, 2 is equal to -1 to the power of 3, which is -1. So this is an odd permutation. Yes. So let us go to the next one, for example number 3. So what's that? So it's 5, 4, 1, and 3, and 2. Yes. So what can I do here? So for example, I can interchange these two. I can interchange one, because 1 is not in its natural position, so I need to move a 1 here, for example. So, but I have to interchange. So 1 goes here, 5 goes there. Yes. So it becomes 1, 4, 5, 3, and 2. Yes. Okay, now for example, what can I do? I can, for example, interchange 5 and 2 together. So it becomes 1, 4, and then 2 comes here, 3 goes there, and 5 goes there. Yes. And then I can interchange 2 and 4. So it becomes 1, 2, 4, 3, 5. And finally, I can interchange 3 and 4. So it becomes 1, 2, 3, 4, and 5. Yes. So it is now in the natural order. So how many steps did it take? So 1, 2, 3, 4. So I would say that the sign of 5, 4, 1, 3, and 2 is equal to minus 1 to the power of 4, which is 1. So what is the permutation? The permutation is even. Yes? So you see that's very actually simple. You shouldn't be distracted by those mathematical symbols. So now finally number 4. So I have 3, 1, 4, 2, 6, and 5. Yes? So what can I do, for example? You see, 1 is not in its own place, so I interchange it with 3, for example. So this becomes 1, 3, 4, 2, 6, and 5. And then, for example, I can interchange 3 with 4, so that 3 be in its natural place position. So it becomes 1, 4, 3, 2, 6, 5. Yes. And then I can, for example, interchange 4 and 2, then both of them will be in their natural positions, locations, yes, these two. So then it becomes 1, 2, 3, 4, 6, and 5. Now, the last one is I just interchanged 6 and 5. So 1, 2, 3, 4, 5, and 6. Yes, and now you see that this is in natural order. So how many steps we needed? 1, 2, 3, 4. So again, what can I write? I can write that the sign of 3, 1, 4, 2, 6, 5 is equal to minus 1 to power 4, which is 1. So it is even. Okay? So determining the sign actually of a permutation is very simple. But let me say, in each case, I try to somehow convince you that what I counted in each case was indeed the minimum number of transpositions needed, as is required by the definition. Yes, if you go back to the definition, you see that this number n to the n is supposed to be the minimum number of transpositions. But of course, I didn't provide any rigorous proof for that. So I think you agree with me that at the end of the process, convincing ourselves that what we have done is the optimal way of doing things, and it would not be possible to do the job in a fewer number of steps is not that easy, especially if the number of terms in the permutation is fairly large. Okay, I have two different types of answers here for you. The first answer is that there is an algorithm that gives you exactly the minimum number of transpositions needed to put a permutation back in order. In fact, I used it in the previous example without mentioning it. And the good news is that this algorithm is easy to follow manually by hand. I will describe it shortly, of course, without proving it. The second answer is that as far as only the sign of the permutation is concerned, we don't need to be worried about if what we count is indeed the minimum number of transpositions needed, thanks to a theorem in abstract algebra. I have explained this remark what I mean this, but let me just describe you the content. You can read it yourself afterwards. Okay? A theorem in abstract algebra guarantees that if by applying successive transpositions on a permutation it is brought back to its natural order, no matter how it is done, in an optimal way or not, the number of transpositions needed is either always an odd number or always an even number. Okay? So what is the benefit of this theorem? It's clear. So as soon as you brought a permutation back to its natural order, you count the number of transpositions you applied. If it is odd, the sign of the permutation is -1. If it is even, the sign of the permutation is +1. And you don't need to be worried at all if the number of transpositions that you count is indeed the minimum number of transpositions needed or not. Okay, for example, let me consider this case. You see, let me consider this case here. Yes, so here the minimum number of transpositions needed was 3, and then you saw that the sign of this permutation is -1 and it was odd. So let me write this here again, but let me be a little bit careless this time. So 1, 4, 3, 5, 1, 2. So assume that I am careless. I am just caring about put them in order without thinking. Okay, so you might do it in this way. So for example, you might interchange 1 and 5. So for example, you say that my goal is to bring 1 here. So you might say that I interchange 1 with 5. So it becomes 4, 3, 1, 5, 2. Then you interchange 1 with 3. It becomes 4, 1, 3. And then you have 5, 2, and then for example you then interchange 1 and 4, it becomes 1, 4, 3, and 5 and 2. So then for example you say that okay, I interchange 2 with 4, it becomes 1, 2, 3, 5, and 4, and finally you interchange 4 and 5. Then finally you got your permutation in its natural order. And then you count. Of course, you see that I was careless, and then definitely you agree with me that this is not the optimal way of doing things. But let me count the number of steps. 1, 2, 3, 4, and 5. Okay? So it means that now, if I am careless and I say that, okay, this is odd, and I get -1, and I would say that the permutation is odd, it is completely correct. Go back and see here. The permutation was indeed an odd permutation. But here, I did it in an optimal way. Here, I did it a little bit carelessly. But the point is that the parity, evenness or oddness, parity means evenness or oddness. The parity of the number of transpositions needed to put a permutation back in its own natural positions is always either odd or even. So if you can do it in an odd number of ways, you have to do it always in an odd number of ways. If you can do it applying even number of transpositions, it doesn't matter how do you do it in an optimal way or not, you have to do it always in even number of steps. Okay, so that is actually the content of this remark that I have written this here for you. Okay, so you can read it yourself afterwards. Okay, so now let me explain you the algorithm that we need here, yes? So let us go to the next example. Determine as the sign of each permutations in example 4 point, I mean the previous example graphically, because you see that I need to draw some graphs if I want to follow the algorithm. Okay, so let us see here. I think for explaining this algorithm, this is not a good starting point. So if you don't mind, let me start from here, then I will go back and then solve it at the end. Yes? So here I have 4, 3, 5, 1, and 2. Yes? So I will have number 2, 4, 3, 5. So let me, yeah, 4, 5, 4, 3, 5, 1, and 2. So the algorithm is like this. You start from the minimum number in your list. Yes, this is 1. Is it in its natural position? The answer is no. Where is the natural position for this minimum number? It's here. Okay, so you do like this. You start drawing an arrow from 1 to its own natural position, which is here. Then you start from this point and see that where the natural position of this one is. Where is it? It's exactly here. So I complete the arrow and I end up with a number that I have already exported an arrow from. So it means that this process ends and I get a cycle with 2 sides. Okay, what the numbers left are these 3 numbers. So what should I do? Again, I find the minimum number left in my list, and which is 2. And I draw an arrow. So let me change my color. I start from 2 and I move it to its natural position. So where is the natural position for 2? It's here. Yes. Okay. And then where is the natural position? I start from 3 again. Where is the natural position for 3? The natural position for 3 is the 3rd place, is here. And then I need to continue until I go to a number such that there is an arrow exported from it already. Yes. So 5, where is the natural position for 5? The natural position for 5 is here, and then I end. So did I cover all the numbers? Yes. All the numbers you see have already been considered. Yes. Either an arrow is exported from them or an arrow is imported to them. Yes. Okay, and then what we do is this. We would write the number, the minimum number of transpositions needed, in this case for 5 numbers, is equal to. You count the number of these edges in each cycle that you actually created. So here I have 2 edges, and here I have 3 edges. So this is the, you need to write 2 edges minus 1. This is the algorithm, it works here in this way. And then you have 3 minus 1. So this is the number of edges involved in the first cycle, minus 1 always. Then the number of edges involved in the second one is 3 minus 1 always. And then you calculate, it becomes 1 plus 2, which is 3. So the minimum number of transpositions needed to put this in order is 3. So it means that this is even. Sorry, it is odd. So sine of 4, 3, 5, 1, 2 is minus 1 to the 3, which is minus 1. And it is exactly according to what we got here. So you see it was. And if you see that even if I carelessly do that, I again find this one. So having the minimum number of permutations is not actually our concern here as far as this sign is concerned. Yes. And if you don't mind, let me just put this a little bit lower to make it clean. No, it doesn't work. Okay. So let us do the other one. So number 3 is this one. 5, 4, 1, 3, and 2. Yes. So number 3. It is 5, 4, 1, 3, and 2. Let me double check. Yes. Okay, so what should I do again? I start from the minimum number in my list. I move it to its natural position. Yes, so where is it? 1 should be here. And then I start with 5. Where is the natural position for 5? It's at the end of my list. Okay, now you see that I have to start with 2, yes, because 2 was not already involved. So where is the natural position for 2? It's here. Okay? And then I start with 4. Where is the natural position for 4? It's here. And then where is the natural position for 3? It's here. So it's only one cycle. Yes. So if you don't mind, let me write this number here in front of you. So I started with 1. From 1 I went to 5. Yes. And from 5 I went to 2. From 2 I went to 4. And from 4 I went to 3. And from 3 I finally went to 1. So let me complete the cycle. Finally I went here. You see? So that creates a cycle. And then there is only one cycle involved. Yes. So the cycle involved, so I would write n5 in this case is equal. There is only one cycle involved. How many arrows are there? 1, 2, 3, 4, and 5. So I would write 5 minus 1, which is 4. And then this means that the sign of this permutation is equal to minus 1 to the 4, which is 1. So it is even. Yes. And then if you go back, we actually, number 3, we found it was even. And if you see, then the minimum number of the minimum number of transpositions needed was actually 4, because I was indeed following the algorithm back in my head. Okay, now let us go to the next one. You see here 3, 1, 4, 2, 6, 5. Okay, so let me just take it here with me and then write it here. So I have number 4. It is 3, 1, 4, 2, 6, and 5. Yes, so let us see what we need to do. I start with the minimum number in my list, which is 1. Where is the natural position for 1? It's here. But I have to start with 3 here. Where is the natural position for 3? It's here. I start with 4. Where is the natural position for 4? It's here. Yes. And then where is the natural position for 2? The natural position for 2 is here. And the cycle is done because I ended on a number from which an arrow was exported. So this gives me a cycle. Okay? Then there are 2 numbers left. What is the minimum number left in my list? It's 5. So where is the natural position for 5? It's here. And then where is the natural? I need to start from 6 now. Where is the natural position for 6? It's here. Yes. So let me, by the way, change my colors here. So 5 to 6, 6 to 5. So if I want to write them again, so I would write it in this form. I would say that 1 went to 3, 3 went to 4, 4 went to 2, and then finally 2 went back to 1. The cycle is complete. And then I had 5 went to 6, and 6 went back to 5. The cycle is complete. Okay, how many edges are involved here? 1, 2, 3, 4. But I write 4 minus 1 plus, how many edges are involved here? 1 and 2. So I would write 2 minus 1. So this becomes 3 plus 1, and it is 4. Yes, so this means that the minimum number I was looking for is just 4. So the sign of this permutation is equal to minus 1 to the 4, which is 1. So it is even again. Yes, but of course the first example was very trivial, but let me just mention it how we can use the algorithm here if you want to. Of course it is very, very trivial. So number 1, it was 1, 2, 3, and 4. So what do? You start from the minimum number in your list, which is 1. Where is the natural position for 1? It's here. So I end up with here. Finished. The cycle is complete now. Then what is the minimum number in my list? Here. It's 2. I have to put it's in natural position, but the natural position is here. The same thing for 3, the same thing for 4. So what is in 4 here? So here the number of edges is 1, so it is 1 minus 1 plus the number of edges, the second one is 1 minus 1 again, 1 minus 1 again, and 1 minus 1, and as you see you get exactly 0. And of course it was trivial, we actually didn't need to do it in the first place. Okay? So I hope that you learned that this is always working, and it is actually very easy to do it by hand. You don't need to do a lot of calculations, or it is not very messy. So it's a very user-friendly algorithm to find the minimum number of transpositions needed to bring any given permutation back in its own natural position. Yes. Okay, before leaving this example, let me mention something in passing. Okay, so for example, here we were able to realize that 4 is the minimum number of transpositions needed to put this permutation in place, in order. So, but now you might ask, okay, how can I write the transpositions explicitly? That's also very easy. So let me just do it here for you. So for example, you have this permutation 3, 1, 4, 2, 6, and 5. 6 and 5. And then you see you want to follow exactly these cycles. Okay? The first thing that we need to do, we need to according to this cycle, we need to interchange 1 and 3 together. So I need to interchange 1 and 3. So what happens? 1 goes here, 3 goes there, and I need to keep everything as before. Yes? Okay, and now go to the next step. 3 and 4 should be interchanged. Here is 3, here is 4, I need to interchange them. So I put 4 here, 3 here, and then I keep everything as before. Yes? And then I go to the next step. 4 and 2 should be interchanged now. Here is 4, here is 2, I interchange them and I keep everything as before. So this 2 goes here, 4 goes there, I will keep 1, 3, and 6, and 5. You see, I will not do 2 and 1 here. I will not interchange them here. This is why we always have this minus 1 at the end. So the number of arrows that you see is 4, but the number of transpositions is actually 3. 1 less. This is the reason that we have that minus 1 there. Yes. Now this cycle is finished. I go to the next cycle. In the next cycle, 5 should be interchanged with 6. So then it means that I need to keep everything as before, but I need to just interchange 6 and 5. Yes, so it becomes 5 and 6, and it's on order. Again, you see that I have 2 arrows involved, but I have only 1 transposition involved, and that's the game because of that. This is why we write that minus 1 here. So, okay, so if you want to write the transpositions explicitly, this is also doable using the same algorithm. Okay, a nice thing that is also a nice diagrammatic way to understand this in a different way. Let me just mention that one as well here. So here we have 6 points. You put 6 dots here, 1, 2, 3, 4, 5, 6, and then you give them names, 1, 2, 3, 4, 5, 6, and then you go and put 6 more dots in a row below. But this time you give them these names in this order. Yes, so I will name the first one 3, the second one 1, 4, 2, 6, and 5. And then what I do now, I connect every point from the row above to the point with the same name in the row below. Okay, so let us do it. So I need to connect 1 to 1. I need to connect 2 to 2. I need to connect 3 to 3. Yes. I need to connect 4 to 4. 5 to 5. And finally, so let me make it clear, 5 to 5, 6 to 6. And then what I need to do is to count the number of intersection points. So this is 1 intersection point, 2 intersection, 3 and 4. Yes? Of course, if you see here, the minimum number was also coincidentally 4. So that's a coincidence. This is not always the case that the number of intersections is exactly equal to the minimum number of transpositions we need. But the point is that the parity of the intersection points is always a correct parity. So it means that if I count here how many points are involved, 4 as in even number, so then I will say that this permutation is an even. Okay? But let me repeat that there are 4 intersection points exactly as the minimum number is a coincidence. Okay? So to see this probably better, let me do one more example. Let us go back to this point. Let me make this a little bit smaller so that we can see everything here. So let us consider this certain case here. So what can I do? I can write them here. So it is 4, 3, 5, 1, and 2. Yes? So let me draw the similar diagram for this one. So if I want to do this, what should I do? Now I can make it bigger. So here I put 5 points. So 1 point, 2, 3, 4, and 5. Yes. And then so I will call them 1, 2, 3, 4, and 5. Then I will put 5 points below. So it is 1, 2, 3, 4, and 5. But I put the names, I give the names in this order. So the first one is 4, 3, 5, 1, and 2. Then I will start connecting them. So 1 to 1. Sometimes it is actually not that easy to draw these diagrams very carefully with hands, so you will see it here. So 1 to 1, and then I have to connect 2 to 2. I have to connect 3 to 3. Gives me this. And then this is a little bit tricky. You see 4 to 4, but by symmetry this is equidistance from 3 and this 4 is equidistance from 3, so definitely this will pass through this point. Yes, but you see it's not that easy to see. This is why I'm saying that still the previous algorithm is much better. Okay, and then I have to connect 5 to 5 itself, and then let me count the number of intersection points here. So this is 1 intersection point, 2, 3, 4, and finally 5. Okay, so 5 is an odd number, so my conclusion is that this is odd. Yes, but if you go back here, you see the conclusion that this is odd is correct. But the minimum number of permutations needed, the minimum number of transpositions needed is actually 3, not 5. Okay, but the good point is that the parity remains the same. 5 is still odd, 3 is also odd. So my conclusion about the evenness or oddness of my permutation is completely valid. Okay, I think that this is also useful to know, even though I would always prefer to use the algorithm, of course. Yes. Okay, now let us go back and finally finalize our definition of a determinant in general. If you remember, the only part in the definition of a determinant that still has to be addressed is to understand when an elementary product comes with a positive sign and when it comes with a negative sign. Now, eventually, we are completely ready to take that final leap. Do you have any clue of how it should be? Yes, but what I have talked about, the sign of the permutation, so forth? Yes, you are right. The sign of each elementary product is positive if the sign of the permutation formed by considering all second indices in that elementary product is 1, and it is negative otherwise. Yes. So for example, assume that you want to know if the elementary product, say for example, if this elementary product A1 3, A2 2, and A3 1 in the definition of a 3 by 3 determinant comes with a positive sign or a negative one. So how we should do? We need to consider, so first of all we need to make sure that this is in order, yes? So the first indices are 1, 2, 3. They are in natural order, yes? And then we pick up the second indices. The second indices in this order are 3, 2, and 1, okay? And then we determine actually the sign of the permutation consisting of the second indices. Yeah, so it was crucial. You have to put the first indices in order first and then pick up the second indices and then look at the sign of that permutation. Yes, so so you see immediately that I can replace these two. So the minimum transposition needed to put this in order is just 1, yes? If I put 1 here and 3 here, then it becomes 1, 2, 3, which is the natural order, so I need only 1. So it becomes minus 1 to the power of 1, which is negative 1. So it means that the sign for this is negative. Why? Because this is an odd permutation. Yes? Okay. Before going directly to the general case of an n by n determinant, let us consider the case of a 4 by 4 determinant first. Okay, and I have written an example for you here. Example 4.1. So consider this determinant, 4 by 4 determinant. Okay. Now answer the following questions based on what we have discussed so far. Yes. So is this, you see I have a 4 by 4 determinant and that's a product of 4 entries of the determinant. Now I am asking, is this an elementary product for this determinant? Yes. So I think it's very clear now for you. So problem number 1. So the answer is negative. Yes. Why? Because you see that here this index, the second index 3, and another second index is again 3. So it means that 2 entries have been chosen from the third column. You see A13 is here, A33 is also here, and they actually lie on the same column. But I told you that any elementary product has exactly one element from each row and exactly one element from each column. So this, what I have written here, is not an elementary product for this determinant. So this answer is just no. Yes. So what about this one? Do you think that this is an elementary product? Yes. So where is A13? So A13 is here. The next term is A21, which is here. The next one is A34, which is here. And finally I have A42. Yes. So if you look at the row point, you see I have exactly one element in each row. And if you look at the columns, I have exactly one element from each column. So yes, the answer to this one is actually yes. Okay, so the answer to the second one is yes. Another way of looking at this is that, okay, you see that I have 1, 2, 3, 4. The first indices actually covers all numbers from 1 to 4 exactly once. And then here I have exactly 1, 1, exactly 1, 2, exactly 1, 3, and exactly 1, 4. So this is actually an elementary product for this determinant. Yes. So what about the next one? Is this also a linear, an elementary product? Let us check. A31 is here. The next one is A14. A14 is here. Yes. And then you have A42. So where is A42? So sorry, I made a mistake. A31 is here, A14 is here, A42 is here, and A23 is here. And again, if you look at the rows, you have exactly one element from each row, and if you look at the columns, you have exactly one element from each column. So that is also an elementary product. Yes. The other way to look at this is that, okay, if you look at the set of the first indices, so let me write, for example, the set consisting of the first indices. So you see, I have 3, 1, 4, 2. So let me write it here. 3, 1, 4, 2. So it covers all the numbers from 1 to 4 exactly once. And if I look at the second indices, I have 1, 4, 2, 3. 1, 4, 2, 3. So again, I have all of them. So yes, the answer to the next one is also a yes. Okay, now if so, determine their signs. Yes, so we want to determine the signs of each one of them. Okay. So let us consider the first one. The first one is in order. So it is A13, A21, A34. When you want to determine the sign, it's very important to put the first indices in order if they are not already in that form. Okay, and then try to see what are the second indices. So the second indices are 3, 1, 4, and 2. Okay, so now I need to determine the sign of this permutation. Okay, so for example, you can use the algorithm that I talked about. So 1 goes to here. Now let me change the color. So 1 goes to its natural position 3, 3 goes to its natural position 4, and then 4 has to go to its natural position 2, and then finally 2 goes to its natural position 1. Yes, so what is this minimum number of transpositions needed? I have 4 arrows, so it is 3. Yes, so it means that the sign of 3, 1, 4, 2 is minus 1 to the 4, which is positive 1. So this should come with a positive sign. Yes, for example, the second one. What is the second one? It's A31, A14, A42, and A23. Yes? So be careful. If you choose 1, 4, 2, 3, it's not correct. It's very crucial. First, you need to put the first indices in order. Okay? So, not by transposition, just reorder them. So I need to write A14 first, and then I need to start with A2, 3, and then A3, 1, and then A4, 2. Yes? And then you need to read the second indices. So what are the second indices now? They are 4, 3, 1, and 2. Now I want to determine the sign. Yes? So what should I do now? 1 should go here, 4 should go here, and then 2 should go here. Yes, and then 3 should go here. So again, how many arrows are involved? 4 arrows are involved. 1, 2, 3, 4. Oh, okay, sorry. I made a mistake in the previous one. 4 arrows are involved. So there are, oops. So 4 arrows was involved. So this is not 4, this is 3. So let me clean this. So sorry for that. So this is 3, and then it becomes -1, not 1. Yes, and then what happens is that this is also, that's my bad, sorry for that. Okay, so the number of arrows -1 is the minimum number of transpositions needed, not the number of arrows. Okay, so here that's also the same here. So I have 1, 2, 3, and 4 arrows. So it means that the sign of this one is also the sign of 4, 3, 1, 2 is also -1 to the 3, which is -1. So again, this comes with a negative sign. Okay. So for example, the second part of the problem, we're supposed to specify two random signed elementary products except the ones that was mentioned in the first part. Yes, so we can just randomly choose them. Let me make it a little bit smaller to put it in front of eyes. I have to choose exactly one entry from each row and exactly one entry from each column. I do one of them and then you can do the other one as an exercise yourself. Okay, so for example, let me change my color here. Yeah, let me change my color to red here. So for example, from the first row, I can pick a random entry, but then I am not allowed to choose this one. So let me cross it over. This is not possible anymore. This is not possible anymore. Yes. Now we go to the second row. In the second column, in the second row, I have three options left. We can choose one of them. For example, let me choose this one. Yes. So then what happens? So let me make it bigger here. I choose this one. As soon as I choose this one, I need to cross these entries away. I also need to cross these entries away. Yes. And then, for example, when I go to the third row, I have two options available. I need to choose one of them. So let me, for example, choose this one, A3 one. As soon as I choose this one, I need to take this one away, and I also need to take that one away. And then you see that I have exactly one entry left. So this is, for example, one possible elementary product. Okay, so let me make it a little bit smaller so that I can write it here in front of your eyes. So it becomes, the first one is A12, the second one is A23, the next one is A31, and the last one is A44. So 1, 2, 3, 4 is already in order. So what is the set of second indices? It is 2 with the same order: 3, 1, and finally 4. Okay, now assume that I want to find the sign of this permutation. So what I can do, I can move 1 here, 2 should be removed to its natural position, 3 should be moved here. Then you see that I have a cycle, and of course 4 is already in its natural position. Yes, so how many arrows are involved? I have 3 arrows, so it means that the sign of this sign the permutation 2, 3, 1, and 4 is just minus 1 to the power of 2, not 3. The number of arrows 1 less. So it becomes positive 1. So then it means that this should be with positive. Yes? And I think you can do the other one yourself. You can choose any other one. But what is important is that all possible elementary products that you can imagine in a 4x4 determinant appears once and exactly once in the definition of the determinant with some prescribed sign that comes from the sign of the permutation of the second indices. Okay, for example, if you want to do the last one, define this determinant by an English sentence without using any mathematical symbols. Yes. So how can I define? I can say that this determinant here is equal to what? Is equal to the sum of all possible signed elementary products consisting of entries of the determinant. as factors, for example. Yes? So it means that if I want to define this 4x4 determinant, I can just simply say the sum of all possible signed elementary products. Yes? It's as simple as that. So then you can immediately see that this is, you see, I haven't referred to the order of this determinant in this sentence at all. You see, the order of this determinant is 4x4. I have just written that the sum of all possible signed elementary products. Of course, it is clear that if I have a determinant of higher order, the number of possible elementary products actually grows, yes, and it grows as n factorial. So if here I have 24 of them. But I think when I want to write the sentence defining my determinant, I do not refer to the number 4 at all. So it means that I can take this as the definition of a generic determinant, not just only 4x4, 3x3, yes. So this will motivate actually the next definition, yes? We are now completely ready to present the formal definition of a determinant as an abstract mathematical entity, and I have presented here for you. So, but now I want to emphasize here, so determinant, as I told in the beginning of the session, is that a number that we assign, we associate with a matrix, a square matrix. So I would say that the formal definition of determinant is this. Let A be a square matrix of order n. The determinant of A is denoted by either this symbol, det of A, or the symbol which is similar to absolute value, but it is not, and is defined to be the sum of all possible signed elementary products that can be formed using the entries of this matrix. So if you want to have a formula for that, so this sentence is completely enough for defining a determinant, but if you want to have a formula for defining your determinant, you can consider this one. So determinant of this matrix A is the sum over all signed elementary products that I can form from the entries of this matrix. You see where the sum is over all permutations J1, J2 up to Jn of the natural numbers 1, 2 up to n. So finally, I hope that I could motivate you with this definition, that this definition is really natural definition coming out of the consequences. So we started from a 2x2 determinant, 3x3 determinant. I got some motivation how to define my determinant in general form, and then now this is, I wouldn't say that this is artificial. Actually, in the context that it was invented in the beginning, it's completely natural to come to this definition. Okay, and then what is the remark that I have mentioned? The sum in this definition, of course, consists of n factorial terms, because for each permutation of these numbers 1 up to n, I have exactly one signed elementary product associated with it. And because the number of permutations of these numbers is n factorial, so I will have n factorial terms in this sum. Okay? Good. Now, I would say that it is instructive, even though I know that you already know it probably, but let me use this definition again to get the definition of a 3-by determinant back. I want to make sure that you really understand what is going on in this. So what's the point? The point is that I have a 3-by-3 determinant, a matrix, A11, A33 finally, and I want to calculate the determinant of that one. So first of all, I need to write a sum, yes? Sum over all permutations of 1, 2, up to 3 in this case. So let me write the permutations. So what are the permutations? So I have, so let me write J1, J2, and J3. This could be 1, 2, 3. This could be 1, 3, 2. Or, so let me separate them. This can be 2, 1, 3. This can be 2, 3, and 1. This can be 3, 1, and 2. And finally, I have 3, 2, and 1. Yes? Now, if I want to calculate the determinant, I would write it in this form. So determinant of A is equal to the sign of the first permutation. So it becomes sign of 1, 2, 3. Then I will write, you see, I will have A1, A2 up to AN. So I will have A1, A2, A3. And then I put this 1 here, I put this 2 here, and I put this 3 here. Yes, so it becomes 1, 1, 2, 2, and 3, 3. Okay, plus, because this sigma means I have to add them. I go to the next one here. What is that one? It is sine of 1, 3, 2, and then I would write 3 A's. The first indices are in order always, A, 1, 2, and 3. And then I put this number here, I put the second one here, yes, and then I will put this one here. So it becomes 1, yes, 3, and 2. Yes, then I will go to the next term. So it becomes sine of what? 2, 1, 3, and then I will have 3 A's again. Again, 1, 2, and 3. Now I put 2 here, 1 here, 3 here. I will go to the next one. It is 2, 3, and 1. So I would write A1, A2, A3. I put 2 here, 3 here, and 1 here. And finally, I would write plus the sign of 3, 1, 2. I write 3 A's here, 1 here, 2 here, 3 here, but this time I put 3, 1, and 2. I'm putting the same order here. So then I will get this one, 3, 2, 1. Again, I have 3 A's, 1, 2, 3 in order, but this time 3, 2, and 1. Yes? So if we go forward, then I need to determine the signs. Yes? So what is the sign of this one? It's already in natural order, so the number of transpositions that I need is 0. 1 to power 0. 0 is even, so I can write it positive. And then I go to here, you see I need one interchange between 2 and 3. So this is 1, so it is negative because 1 is odd. And then here I only need 1, so this is also odd. Here I need 2, yes? Yes, I need 2. 2 is even, so it becomes positive. So here I need how many permutations? So 2 again, so it's also positive because 2 is even. And then here I have 1, because if I just interchange 1 and 3, everything is in order, so I will get this one 1, and 1 is odd, so this becomes negative. And then you can immediately see that if you contain these positive signs, so you will have your definition of your determinant. So I don't write all of them, but you will immediately see that the first one is A11, A22, A33 with positive signs. For example, the next one is A11, A23, A32. The other one is also negative, A12, A21, A33, and then you can continue this list. Okay? So this is, I think, instructive if you see that how we can immediately actually produce the definitions that we have agreed on so far by using this new definition. But now the good point of this definition is that we are not restricted to only 3 by 3, 2 by 2, 4 by 4 determinants. We can define all possible determinants of all orders. But before going any further, let me mention that this formula is extremely inefficient if the goal is to compute the value of a given determinant. By the way, it's inefficient not only for us as humans, but also for computers. Of course, it is valuable from theoretical point of view. Using this formula, we can extract very interesting properties of determinants, and using these properties, we can compute determinants of higher order much faster. Let me provide you with some details here. One way to compare the efficiencies of different algorithms that are supposed to do the same task is to compare the number of operations, arithmetic operations, required for an algorithm. Okay, so this motivates the following definitions. Okay, so definition. Flop and cost. An arithmetic operation, addition, subtraction, multiplication, division, on two real numbers is called a flop in computer jargon, an acronym for floating point operation. Okay, so that's the meaning of a flop. So if you add two numbers, that is one flop. If you add two numbers and subtract the next number from it, it's two flops. Yes? And the total number of flops required to follow an algorithm is called the cost of the solution, or the cost of the algorithm. Okay? So let us see why calculating determinants using this formula is very costly from computational point of view. Okay, so here I have asked in this example, determine the cost of computing an n by n determinant using an algorithm that follows from the given definition. So we want to see how costly is that from computational point of view if I want to calculate a determinant using this definition that we motivated here. Yes? Okay, now let us calculate the cost of computing an n by n determinant. So what I mean is to calculate the number of arithmetic operations that one can execute to be able to calculate an n by n determinant based on the definition. So if I have an n by n determinant, for example a11 up to ann, yes, so that would be a sum of some elementary products, a11, a22 up to ann, and then I don't know, you have different different elementary products that you want to add them. But how many terms are involved here? You have n factorial terms involved. Okay, but how many arithmetic operations do I need for doing one elementary product? In each elementary product, I have n factors. So the number of operations, the number of products that I need is just n minus 1. Yes, so I need n minus 1 products here to perform this one. And the same thing here, n minus 1 products, all of them are n minus 1 products. So I have n factorial terms. Each term involves with n minus 1 products. So in total, how many products I have to apply? I have to calculate n factorial times n minus 1. Okay? And then I need some additions or subtractions at the end. How many of them? I have n factorial terms here. So the number of addition and subtractions in total is 1 less than this one. Yes, for example, if you want to add 3 numbers, something like this, the number of summands is 1 more than the number of operations. Here I have 3 summands, but the number of operations involved is just 2. So it means that the total number of addition or subtractions that will come next is n factorial minus 1. Yes, so this is this number plus n factorial minus 1. So this is the total cost for calculating an n by n determinant using this definition. Yes, so if I simplify this a little bit, I multiply this inside, so this becomes n times n factorial minus n factorial. Then I will have n factorial minus 1. This n factorial and this one are gone, so the total cost is n times n factorial minus 1, and that's a huge number. So you know that factorial even dominates exponentials. Yes, so probably in your calculus course you have already seen that. So if a is a positive number, if I calculate the limit of a to power n and divide it by n factorial when n goes to infinity, this limit is indeed 0. So it means that this grows much faster even than an exponential. Yes. So when the computational cost of an algorithm is growing by factorial, it means that it is not efficient at all, even for computers. So for example, if I want to have a rough estimate, according to what I could find on the internet, a typical today's PC is capable of performing nearly 10 to the power 10 flops per second. Yes, so the speed of calculation for a normal PC is roughly 10 to the 10 flops per second. Yes, assume that you want to calculate a 30 by 30 determinant. Yes, so n is 30. So the cost for this calculation is equal to 30 times 30 factorial minus 1. That would be the cost of that calculation. So let us see how long will it take for a normal PC to calculate a 30 by 30 determinant, roughly, of course. Yes. So what would be the time? The time that will pass is 30 times 30 factorial minus 1. Then I divide this by 10 to the power of 10. This of course gives me seconds. If I divide by 8,640, this is the number of seconds in a day. This will give me the days, and if I divide by 365, it gives me the number of years. And I used a computer to calculate. If you do that, it would be of order of 10 billion years or more. So 10 billion years. 10 to the 10 to the power of 10 years, which means 10 billion years. Okay, so it's a very huge number. So you see that this is actually very inefficient even for computers. So if the computers want to follow exactly this definition to calculate these determinants, if they want to calculate a 30 by 30 determinant, it takes more than 10 billion years for them to finish the calculation. Okay, but of course computers can do it much faster. The reason is that using this definition, using this abstract definition, we will be able to extract some properties of determinants that will facilitate the job of calculation of determinants as well. Okay, so this is why I'm saying that this definition, even though computationally inefficient, but it is theoretically very valuable. Yes. So then I will come to them to these points later when in the future lectures. Okay, so we now use this definition of determinant to prove two very handy theorems for determinants. Okay, so they are very simple but very important. Okay, so one theorem, Theorem 4.16, the determinant of a matrix, of a square matrix that contains a 0 row or a 0 column is 0. First, let me mention what do I mean by 0 row. a row in a matrix such that all the entries are equal to 0 is, I call it a 0 row. Similarly for a 0 column. If I have a column whose entries are all 0, then I will call it a 0 column. So this theorem tells you that if you have a square matrix containing a 0 row or a 0 column, then you really don't need to calculate the determinant through that definition. That definition gives rise to 0 immediately. Okay, so understanding this is very simple. So let me write the proof for this theorem. But it's very simple to understand. So for example, let us consider that you have this is your matrix A, you have a 0 row, for example. And so I have A1, 1, then I have A1, 2 up to A1n. And then for example, at some point here you have all zeros, and then you have again AN1, AN2 up to ANN. Yes? So if you want to calculate the determinant using the definition, that is a sum of sine of J1 up to Jn, then you have elementary products A1J1, yes, and then up, so let me write one more term, A2J2, and it goes up to ANJN, yes, and I told you that each elementary product that you consider, no matter which one you are considering, it contains exactly one element from each row. So for example, consider this typical elementary product. According to that idea, exactly one of these factors should be chosen from this row. Yes? So then it means that because of that one single zero, at least in this product vanishes. And the same thing can happen, that actually happens for all elementary products. So it means that I have a sum of elementary products, but each elementary product is indeed equal to 0, so the sum of some zeros, a number of zeros, becomes 0 at the end. As simple as that. Instead of if you have a 0 column instead of have a 0 row, then that is the same thing, because again each elementary product contains exactly one single element from each column. Then definitely it will also have an entry from the 0 column. Then again, for the same reason, this product becomes 0 and the sum of zeros is 0. Yes, so you see that this is very handy in proving this theorem. Yes. Okay, for example, based on this theorem, we for example have these two. You see, here I have a 3 by 3 matrix. I want to calculate the determinant, but immediately I see that I have a 0 row, because all entries of this row is equal to 0. I don't need to calculate anything at all. I just immediately say that this is 0. And for example, this 5 by 5 determinant, in principle, if you want to calculate it using definition, you have 5 factorials elementary products, which is 120 terms. But you immediately see that you have a column, a 0 column, a column whose entries are all 0. You don't need to calculate anything at all. By this theorem, the answer is 0. Okay? Now let us go to the next theorem that also can be proved by this definition very efficiently and easily. And that's a very important theorem, by the way. So the determinant of any triangular matrix, yes, is the product of the entries on its main diagonal. Okay, so that's a very important theorem. So here, for example, so it means this is the main diagonal. Any element above that is 0. So if I put a big 0 here, so it means that the possible non-zero numbers are all below this. So this is called a lower triangular matrix. It might happen that I have this bunch of zeros below the diagonal, and the non-zero entries are possibly above this one, then it becomes an upper triangular matrix. But it doesn't matter if it is a lower triangular matrix or an upper triangular matrix. If I want to calculate the determinant here, instead of calculating n factorial elementary products, I can simply multiply these numbers, and then what I get is the exact value for my determinant. So in principle, I can only calculate one elementary product, and that elementary product is the product of the entries on the diagonal. Yes? Okay, so let us first prove this theorem. And I can prove it for the lower triangular, but you can immediately realize that you can prove it for the upper triangular matrices as well. Okay, so here again, let me call this one A. I want to calculate the determinant of A, and I know that the definition is the sum of all signed elementary products. Yes. So A1J1, A2J2 up to ANJN. Yes. But most of these elementary products, probably you expect they become zero, because I have a lot zero entries. But let us see how many of them actually survive. Okay, they have the chance to survive. They have the chance not to vanish. Yes. Okay. I told you that each elementary product contains exactly one entry from each row. So definitely any one of them that you look at has one entry from the first row. Okay? If you take this entry from the first row, forget about that elementary product. The product is zero. If you choose this one, the product is zero. So if you want to give it a chance not to vanish, the only choice left for you is this one. Yeah, so let me write it in this way. So if I want to see which elementary product will survive, I need to choose this one from the first row. Okay, but as soon as I choose this one from the first row, I am not allowed to choose any one of them because they are on the same row as A11 is. And I am not allowed to choose any one of them because they are on the same column as A11 is. So, okay, now let us see how many, so I need to choose another one from the second row. Okay, again, if I choose these ones, of course those elementary products will definitely be zero. So if I want to give it a chance not to vanish, if A22 is not zero, then I have to choose A22, yes? So this is my choice for the entry coming from the second row. But then, as soon as I choose this, I'm not allowed to choose these ones because I told you that each elementary product contains exactly one element from each row and each column. So I'm not allowed to choose these ones. Now I go to the third one, to the third row. What can I choose for the third row? I am not allowed to choose this one and that one because I have already chosen these two from the first two columns. And if I choose these one again, I will get a zero elementary. So if I want to give it a chance not to be zero, then I will have to choose A33. Yes, and then I'm of course not allowed to choose these ones nor those ones. Yes, so you can continue this process and you will see that you will have this one. You are not allowed to choose these, not that one, and if you continue, what is left for you is here. Okay, so there is only one elementary product left, so this means that this sigma will boil down to only one elementary product. That is A11, A22, A33 up to ANN, and the sign is the sign of which numbers? The second indices, 1, 2, 3 up to n. Yes, so 1, 2, 3 up to n. But what is this sign? It's very simple. It's the number of transpositions that I need to put this back in the natural order, but this is already in the natural order. So it means that I don't need to do anything at all. So it becomes the number of the number of transpositions needed is 0. 0 is an even number, so this means that this permutation is even, so this is positive. So then it becomes positive, and I don't need to write that positive one, so it becomes A11, A22, A33 up to AN. And you can immediately exactly follow the same method to prove that this is also the case if you have an upper triangular matrix. And by the way, if you have a diagonal matrix is simultaneously upper triangular and lower triangular, so that is actually expectable. So what I mean is that, so we can write this as a remark. So if I have this determinant d1, d2, d up to dn, and everywhere else is 0, this is a diagonal matrix, but this determinant is also equal to d1, d2 up to dn. You multiply all these entries. Yes? Okay, so for example, if I ask you to calculate this determinant, you immediately see that this determinant is a lower triangular. Why? Because if you draw the main diagonal, all the entries on top of that is actually equal to 0. So that is a lower triangular matrix. So if I want to calculate determinant, I can simply multiply the entries on the main diagonal, and then it will give you 1. So the determinant is simply calculated to be 1. And then let us go to the next one. So here, if you look at this main diagonal, of course you have some element above that equal to 0, but that's not important. What is important is that everything below the main diagonal is equal to 0. So this is an upper triangular matrix. But this theorem also works for upper triangular matrices. So if I want to calculate the determinant, I have to multiply the elements on the main diagonal together, yes? So this becomes 2 times minus 3 times minus 1 times 6. So it becomes 36. Okay? Okay, so we are finished for this video. If you found the video helpful and enjoyed watching it, I would appreciate it if you could give me a thumb up, and I would appreciate you support me by subscribing to my channel. Until the next video, be safe and goodbye.